Imagine a point in space where the known laws of physics cease to function, where time and space themselves are warped beyond recognition, and matter collapses into a realm of unimaginable density. Welcome to the world of singularities, one of the most profound and enigmatic phenomena in the universe. From the mysterious depths of black holes to the very beginnings of the universe itself, singularities challenge everything we think we know about the cosmos, pushing the boundaries of human understanding in ways that we can barely comprehend. But what exactly is a singularity? Why do these bizarre and seemingly impossible objects exist in the universe? Could they hold the key to unlocking some of the most fundamental secrets of physics, perhaps even leading to the next great revolution in our understanding of reality itself? Today, we're going to take a deep dive into the concept of singularities, from the catastrophic collapse of stars that leads to the formation of black holes to the very birth of time and space in the Big Bang itself. As we embark on this journey, we'll unravel the mysteries behind these mind-bending phenomena and explore how singularities challenge some of the most cherished principles in physics. By understanding singularities, we could be one step closer to answering some of the universe's biggest questions. In the vast and intricate fabric of the universe, singularities stand out as some of the most profound and mysterious objects. These are points where the physical laws that govern everything, from the smallest particles to the largest galaxies, completely break down. Here, densities skyrocket to infinity, and space-time itself becomes so distorted that our best mathematical models fail to describe what is happening. For decades, singularities have fascinated physicists and cosmologists because they represent points where our current understanding of the universe, rooted in the general theory of relativity, ceases to be valid. Singularities are not just theoretical curiosities found in equations. They are predicted to exist at the core of every black hole and possibly at the very beginning of the universe, where the Big Bang itself might have originated from a singularity. As we move forward, we will explore the nature of singularities in greater depth. We'll look at the different types of singularities that exist, such as those found in black holes and the Big Bang. Additionally, we will explore why singularities pose some of the most challenging and thought-provoking questions in modern physics. Singularities are where physics, as we know it, meets the edge of the unknown, and understanding them could help unravel the deepest mysteries of the cosmos. At its most basic definition, a singularity refers to a point in space-time where certain physical quantities, such as density, temperature, or the curvature of space-time, become infinite. In physics, this creates a scenario where our current understanding of the laws of nature breaks down, making it impossible to describe the environment using conventional means. Singularities are places where the universe becomes so extreme that the math gives us infinities as answers, signaling that something truly strange is happening and that our existing theories are no longer sufficient to describe the reality. Singularities are fascinating because they represent the ultimate limit of what we can currently understand using the language of physics. They are, in a sense, the boundaries of the universe's ability to be comprehended by the human mind, or at least by the mathematical models we've developed so far. When we encounter a singularity in the equations of general relativity, it means we are facing conditions of such extreme gravity, energy, and density that our theories can no longer cope. In other words, singularities are the places where the known laws of physics break down, and something new is needed to describe what happens at those extreme scales. There are two main contexts in which singularities are typically discussed: the singularities found inside black holes and the Big Bang singularity, believed to have existed at the very start of the universe. These two examples represent the two extremes of our universe. One is about the death of stars, and the other is about the birth of everything we know. The most well-known type of singularity arises in the heart of a black hole. According to the general theory of relativity, when a massive star reaches the end of its life and can no longer support itself against its own gravity, it collapses in on itself. If the star is massive enough, it can form a black hole, a region of space where gravity is so strong that not even light can escape. Once something crosses the event horizon of a black hole, it is pulled inevitably toward the singularity at its center. Surrounding the singularity is the event horizon, the invisible boundary beyond which nothing, neither matter nor light, can escape the overwhelming pull of the black hole's gravity. The event horizon acts as a kind of point of no return. For anything that passes this boundary, the pull toward the singularity is as inevitable as the flow of time itself. This is why black holes appear black. Nothing, not even light, can escape the gravity of the black hole once it has crossed the event horizon. Inside the event horizon, space-time is dramatically curved, and gravitational forces become so intense that all known laws of physics cease to apply. At the singularity, densities become infinite, and the very fabric of space and time is torn apart. All the mass and energy inside the black hole is thought to be compressed into an infinitely small point, creating what we call a singularity. However, this description poses serious problems because infinities like this do not make physical sense. This is why physicists are searching for a new theory, one that can explain what really happens inside a black hole. In addition to traditional black holes, which are known as Schwarzschild black holes, there are other types of black holes, such as Kerr black holes, which rotate. The singularity at the center of a Kerr black hole is thought to take the form of a ring rather than a point. This introduces even more interesting possibilities, such as the theoretical existence of wormholes and even the potential for time travel. The other type of singularity we encounter in physics is the Big Bang singularity, which is thought to have existed at the very beginning of the universe. According to the Big Bang theory, the universe started as an extremely hot, dense point and has been expanding ever since. But what happened before the Big Bang? The theory suggests that at the moment of the Big Bang, all the matter and energy in the universe were compressed into an infinitesimally small, infinitely dense point, a cosmological singularity. At the time of the Big Bang, the entire universe was thought to have been compressed into this singularity, and time, space, matter, and energy all came into existence from this event. However, the exact nature of this singularity and what might have caused the Big Bang remains one of the greatest mysteries in physics. Both types of singularities, gravitational and cosmological, are where physics meets the unknown. To truly understand them, scientists believe we need a new theory that can unite the laws of general relativity with those of quantum mechanics. This new theory, often called quantum gravity, may one day unlock the secrets of singularities and help us answer the most profound questions about the nature of reality. Singularities aren't only confined to black holes. They also play a crucial role in our understanding of the universe's origins. The most famous of these is the Big Bang singularity, theorized to have existed at the very beginning of time and space. According to the Big Bang theory, the universe started as an extremely hot, dense point, and it has been expanding ever since. But what happened before the Big Bang is one of the greatest mysteries. At the moment of the Big Bang, all the matter and energy in the universe were compressed into an infinitesimally small, infinitely dense point known as a cosmological singularity. The Big Bang singularity forces us to confront the limits of our understanding. It marks the beginning of space and time. Since time itself began with the Big Bang, asking what came before is tricky because time as we know it didn't exist. As the universe expanded from this incredibly hot and dense singularity, it cooled down, leading to the formation of matter and energy, and eventually stars and galaxies. But the nature of the singularity and what triggered the Big Bang remains one of the most profound mysteries in physics. The singularity challenges our theories because it represents a point where the laws of physics break down, particularly general relativity. General relativity describes how gravity works on large scales. But at the Big Bang singularity, general relativity predicts infinite densities and temperatures, values that don't make sense physically. These infinities show that our current understanding of physics is incomplete. To solve this, scientists are searching for a new theory that combines general relativity with quantum mechanics, often referred to as quantum gravity. Quantum gravity is needed to explain what happens at singularities like the Big Bang. Two well-known theories in this area are string theory and loop quantum gravity. String theory suggests that the fundamental building blocks of the universe are tiny, vibrating strings, not point-like particles. These strings could explain the Big Bang as something other than an infinitely dense point. Loop quantum gravity proposes that space-time is made up of tiny, discrete loops. In this theory, space and time aren't continuous but come in small chunks. At the Big Bang, these loops might smooth out the singularity, preventing infinite densities. Another question arises: what existed before the Big Bang? Some theories suggest the universe might go through cycles of expansion and contraction, known as cyclic models. In this view, the Big Bang wasn't the beginning of everything, but the latest phase in an endless cycle. This leads to the Big Bounce theory, where the universe bounced from a previous contracting state into expansion. Despite progress in physics, the Big Bang singularity remains an unsolved mystery. It reminds us that there are still deep, fundamental questions about the universe waiting to be answered. Now, let's talk about naked singularities, one of the most fascinating and controversial ideas in modern physics. Unlike the singularities found in black holes, which are hidden behind an event horizon, naked singularities are not. They exist without being cloaked by an event horizon, meaning they could theoretically be observed directly. This challenges one of the core principles of black hole theory and could have significant implications for our understanding of the universe. In the standard model of black holes, the singularity, the point where density and gravity become infinite, is always hidden behind an event horizon, the boundary beyond which nothing, not even light, can escape. This prevents us from observing what happens inside the event horizon. This idea is part of the cosmic censorship hypothesis proposed by physicist Roger Penrose in 1969. The hypothesis suggests that singularities are always hidden behind event horizons, shielding the universe from their extreme and unpredictable effects. However, naked singularities defy this rule. If one existed, it would not be hidden behind an event horizon, meaning its effects could be visible from the outside. This would expose a region where the known laws of physics no longer apply, leading to unusual and potentially chaotic phenomena. What is a naked singularity? In black holes, the event horizon serves as a barrier that prevents us from seeing the singularity. Inside the event horizon, gravity is so strong that everything is pulled toward the singularity, and no information can escape. But with a naked singularity, this barrier would be absent, meaning we could observe the extreme gravitational effects. Near a naked singularity, gravity could become infinite, and space-time might be torn apart. Light and matter near the singularity would behave unpredictably, warping and bending in response to the intense gravitational pull. This could create strange gravitational lensing effects, distorting the light from stars and galaxies behind it. These effects might allow us to observe things normally hidden by a black hole's event horizon. If naked singularities exist, they would challenge our understanding of general relativity. General relativity predicts that singularities should always be hidden behind event horizons, so their existence would suggest that our current understanding of gravity is incomplete. How do naked singularities form? One possibility is that naked singularities could form if a collapsing star rotates fast enough. The centrifugal force might prevent the formation of an event horizon, leaving the singularity exposed. This would result in the star collapsing into a singularity without the protective barrier of an event horizon. Another possibility comes from string theory, which suggests that the universe might have more than 3 spatial dimensions. In these higher dimensional spaces, gravity might behave differently, allowing a singularity to exist without an event horizon. Some physicists believe the cosmic censorship hypothesis may have exceptions, meaning naked singularities could form under extreme conditions. However, these ideas remain speculative, as no naked singularities have been observed yet. What would naked singularities mean for physics? If we were to discover a naked singularity, it would have a huge impact on physics. First, it would violate the cosmic censorship conjecture, a foundational idea in black hole theory. It would also expose regions of space-time where the laws of physics, particularly general relativity, no longer apply. This could lead to the development of new physics, as scientists would need to create theories to explain what happens near a naked singularity. Naked singularities might also provide insights into quantum gravity, the theory that combines general relativity with quantum mechanics. Studying them could help physicists understand how gravity and quantum effects interact. Despite these possibilities, no naked singularities have been observed yet. Astronomers continue searching for them using gravitational wave detectors and space telescopes, but they remain elusive for now. Thank you for watching our content. If you enjoyed this video, please like it and follow us for more updates on space exploration.